Okay, let's start. It's a pleasure to have Semyon Dyatlov today, who's in MIT. Thank you very much for getting up early. And Semyon will lecture about the fractal uncertainty principle. So I didn't mention the name in my lecture, but I stated an estimate which comes from the fractal uncertainty principle. And next time in January, I will explain a bit more how it is used to prove that semi-classical measures have full support.
Bonjour, merci beaucoup pour m'inviter à parler ici. Désolé que je pouvais pas venir à Paris. Quand même, c'est un honneur à être invité à parler à Collège de France. So, okay, I'll switch to English for the math part. So I'll talk today about the fractal uncertainty principle. So I will not actually describe in detail any applications to quantum chaos. Instead, I'll focus on that statement as a statement in itself. And the statement, roughly speaking, is that no function can be localized in both position and frequency near a fractal set. So of course, I'll have to make it much more proper later. But that's a rough idea of it. When if you interpret the usual uncertainty principle as saying that no function can be localized in both position and frequency near some fixed point. Right, so the main applications of these two to date are lower bounds and massive eigenfunctions that maybe will be covered in some later lectures in this series. On compact surfaces, and also spectral gaps on non-compact surfaces. But as I said, I'm not going to go into the applications today. But the general applications are to quantum chaos, and the fractal set appears naturally there, in some sense, out of the dynamics. So I will discuss the proof of the quote-unquote big theorem a bit, but mostly I'll try to focus on the simpler case of discrete countersets, where everything can be written out more simple and more simply and more explicitly. And there I should be able to give a very good idea of the proof. I also wanted to mention, I don't know if there is a way to provide that, but I'll put the slides on my webpage so that anybody can access them, because there might be a bit more on the slides that I'll be able to actually cover today. Okay. I also should stress that the most fractal uncertainty principles known are for subsets of the real line. And a general fractal uncertainty principles in higher dimensions is an open problem. And I think a pretty interesting one, both from the point of view of applications to quantum chaos, but also as a harmonic analysis statement. I personally find it fascinating. All right, so I'll discuss that at the very end. Okay, so here is the setup. So I'm going to do harmonic analysis on the real line in the beginning. And I'll use the semi-classically rescaled version of the Fourier transform. So this means that when I take my Fourier transform, I'm going to divide the argument by h. And h will be a small parameter called the semi-classical parameter. So what this means is that the semi-classical Fourier transform at the frequency of order 1 really corresponds to the original Fourier transform at high frequency of order h inverse. So it's a high frequency question about the Fourier transform. And then I rescale it so that it's a unitary operator on O2. So the formula is here. Then for applications to Laplacian eigenfunctions, actually, this parameter h should be 1 over square root of the eigenvalue. That turns out to be the effective wavelength at which eigenfunctions oscillate. And I believe h appeared before already in previous lectures in this series. So that's the h. So that's the Fourier part, or the harmonic analysis object that we'll use. And then I should also specify what's called by a fractal set, because there are many definitions, and the specific definition that I'll use is called porosity. So let me first give the definition and then discuss it. So if you have a, let's fix a constant nu positive. And then we say that a set, subset of the real line, typically closed subset, is nu porous up to scale h, if for each interval of size between h and 1, there exists a subinterval of relative size nu, so nu times the size of the original interval, which doesn't intersect our set. Okay. So it's a quantitative version of being nowhere dense. Right? So if a set is nowhere dense, means that each interval contains a subinterval which doesn't intersect the set. Now here, I want the size of the subinterval to be some fixed proportion of the size of the interval that is contained in. And I only need to require it for a range of scales. So my intervals don't need to be too big. They can be at most unit size. And they also shouldn't be too small, or they don't have to be too small. They can be size at least h. They should be size at least h. So here, the way you should think about it, there is this h and nu and x. What will happen in practice is that nu should be frozen, independent of h. So say lower bound on massive eigenfunctions, you fix a non-empty open set somewhere, a macroscopic set, and then that actually determines what nu is. And then you let h go to 0. Okay, so nu will be some fixed constant. It could be small, but it can't vary with h. Then h will go to 0, and the set x can depend on h. A typical example that you should think about is that let's take a set which is porous up to scale 0, so really thin set, and then let's take its h, epsilon h neighborhood, and that will have this porosity property. And that's roughly speaking the kind of sets that the theorem would be applied to. And the sets x0 will be defined from the dynamics. Now, here's an example. So the mid-third Cantor set, perhaps the world's best-known example of a fractal set, and it is porous up to scale 0 with constant 1/6. If you want to amuse yourselves, you can show that it's porous actually with any constant strictly less than 1/5. So you see in black here, I drew the Cantor set. It's hard to draw a measured 0 set, but hopefully you'll forgive me. So it's an approximate rendition of the mid-third Cantor set. And you see, I take some blue interval, and no matter where I take my blue interval, and no matter how small it is, I'll always be able to find a green subinterval of size at least 1/6 the size of the blue interval, which doesn't intersect my set. Right? So you see, it's an interesting property because it's a property that's required for a big range of scales. Well, for things like the Cantor set, it's true for all scales. And it's required at all points. Okay. All right. So that's a definition of a fractal set that I will use. Now, let me go on. So here's a statement of the theorem, the quote-unquote big theorem, because there will be some other theorems presented, but that's it, the main one in this lecture. So this is due to Jean Bourgain and myself a few years ago. So let's assume that we have two nu porous sets. And again, you should think of nu being fixed, h going to 0, and the sets can depend on h. Then we have the following estimate. So the left side of the estimates is an L2 to L2 norm. And what you do is you take the semi-classical Fourier transform and you squeeze it between multiplications by indicator functions of these two sets. Okay. So it's easy to see that if the sets have positive measure, which they usually have in our situation, then if you just put one cutoff next to fh, fh is unitary. If you just put one cutoff next to it, you still get an operator of norm 1. But if you squeeze it in between these two cutoffs, then you get something of norm no more than 1. And the statement is that this actually decays, this norm, at a rate like some positive power of h. And the constants here in this rate only depend on the porosity constant and don't depend on h and don't depend on the sets. All right. So that's a statement that's kind of convenient and it's symmetric, but it uses a semi-classical Fourier transform. So here's a restatement of it in more standard harmonic analysis terms. you can see that if I take this triple product and I apply it to any function, well, so I start with some L2 function. Then I apply this indicator function of y. So this just gives me a function supported in y. Then I apply the semi-classical Fourier transform. So what I get is I get a function. The support of whose Fourier transform up to a sign switch is inside h inverse times y because of the semi-classical rescaling. Okay. So if I take any function and I apply these two of the three operators, the two operators on the right to it, I'm going to get something with Fourier transform supported in h inverse times y. So you should think of y as being, let's say, an interval 0, 1. And then h inverse times y is interval 0 to h inverse. Okay, so it's a high frequency set, right? And so that gives you this Fourier support restriction. And then I apply the indicator function of x, and I want this to recover only a small portion of the L2 norm of f. So it's an equivalent statement here. So what this means is that you impose a Fourier localization requirement on your function, and then you want to make sure that the amount of mass on your function on the set x is small. So that's why you can think of it as a version of an uncertainty principle, because if you have the first condition tells you that your function is localized in Fourier space to this set, and then you're ruling out the situation where the function is also localized in position to the set x. Okay. So that's a kind of uncertainty principle. You cannot be localized in Fourier space to the set y and also have a big mass in the set x. And both of those are fractal sets. And again, if you think about scales, you should think of h inverse times y as a union of unit size intervals, which are somehow fractally distributed. But this 1xf is, you should think of it as a union of h-sized intervals, which are also fractally distributed. So that's for the harmonic analysts in the audience, that's the kind of scaling that we're thinking about. All right. So here are some basic things you can say. So when you have a statement like that, you first think, well, what can the standard methods give me? And they give you something, and they give you something essential, but they don't give you this theorem, otherwise this talk would be shorter. So you're looking for this kind of estimate. Now, what kind of beta can you get? Well, of course, you can get beta equals to 0 always, because you know that the Fourier transform is unitary and the other two operators have norm bounded by 1. So this norm is always bounded by 1. Another thing you can do is you can try to argue by volume. So imagine if x and y were h neighborhoods of delta dimensional sets, then we would expect the measures of x and y, the back measures, to be of size h to the 1 minus delta. And then here is a one-line, or well, in Beamer slides, two-line proof of uncertainty principle with the power h to 1/2 minus delta. Okay, it just uses the Holder inequality twice and uses the L1 to L infinity norm bound for the semi-classical Fourier transform. Right? So that's what you get. And then you see that if your sets x and y, for example, if your sets x and y are points, then delta is equal to 1, right? Well, there are h neighborhoods of points. Then delta is equal to 1, and you get h to 1/2 as your norm. And so that recovers a version of the standard uncertainty principle when you're localizing next to points. But in general, this thing works, or it gives you an interesting result when you have sets of dimensions strictly less than 1/2. Somehow, morally speaking, I believe that this sets of dimension less than 1/2 actually corresponds to entropy bounds that you heard about before. The fact that you get less than 1/2 of the total entropy, or you cannot have less than 1/2 of the total entropy in the measure. That being said, I don't think anybody figured out how to actually use the volume bound to prove a sharp entropy bound. But morally speaking, if you look at at least the original proof of entropy bounds in Anantharaman's 2007 paper, you will see that there is a triangle inequality used at some point. And if you think about it, the dispersive estimate would correspond roughly to the situation where x and y are just two intervals of size h. And then when you put them all together, that's the volume bound that you get. But again, this is not, I don't know how to recover the sharp Anantharaman. I'm not sure entropy bound for this. I should say that if we only know the volumes of the sets x and y, then these results cannot be improved. So for example, if you put x and y to be equal to intervals of size square root of h, then it's not hard to see that you cannot get anything interesting out of it. You cannot get beta bigger than 0. That's because the semi-classical Gaussian e to the minus x squared over 2h, it lives in position and frequency pretty close to these intervals. So in order to get an improvement, it's not enough to know the volume. Okay, so it's not going to be some kind of smart argument with using holders several times. You need to know more. You need to know more about the structure of these sets to actually prove a bound like that. And the structure for us comes in the form of this porosity, which is a requirement of having a lot of holes at different scales at different places. All right, so this is what kind of basic observations tell you. Now, let me spend a couple slides briefly talking about the proof. So the proof is quite, it's not that long actually, but it does use some hardcore harmonic analysis, which neither I nor, surprisingly, my collaborator knew before the project started. Well, at least some of it, the kind of the key component, he also had to look it up in a paper. So here's the theorem restated as before. Now, what we have is the following. So we'll deal with x first, the x part first here, the porosity of that, and then we'll use the porosity of y. So how do we use the porosity of x? Well, as I said, it had a lot of holes at a lot of different scales. So what you can do is you can discretize it on a kind of a dyadic sequence of decreasing scales, starting at scale 1 and going all the way down to scale h. And then at each scale, you're going to have this kind of hierarchy of sets, or a nested collection of sets. Their intersection contain, x is contained in their intersection. And each of these sets has new holes at scale 2 to the minus g. So what we'll show is that when you localize your f in position to the next set, you lose a certain fixed proportion of mass compared to the previous set. I'm lying here. The actual proof has to do something slightly different with a cutoff function, but let's say this is how it works. Okay, so you want to know that every time. So you're starting at, let's say you start at scale 1. You just started on the whole line. Well, the norm of L2 on the whole line is equal to itself. Now you go to the next scale and you say, okay, I took out some holes from my set, and I want to see that the mass that I retain is strictly smaller by some fixed relative constant than the mass I had before. So if I can prove that, then I go to the next level. I say, okay, when I look at the next scale iteration of my set, or approximation to my set, I have all these new holes which are on finer scales. And I want to use the fact that I have these new holes to see that I have an even smaller norm bound compared to the previous set. It's a subtle argument, so there are some details missing that might be confusing, but I'll leave it at that. But what you reduce ultimately is that you have to show, so when you're doing this, showing an upper bound on the on how much is left is the same as showing a lower bound on what was removed. So on what was removed in the holes. And so this reduces, after some rescaling and some more arguments, this reduces the whole theorem to the following key lemma. Here's the key lemma. So assume that, so I'll just state it for scale 1, because it turns out you can rescale it to make it work on any relative scale, from one scale to the next one. So assume that I have a collection of intervals of small size but fixed size called alpha. And each of them is in one of the integer intervals. So I take inside interval 0, 1, I take a subinterval of size alpha, inside of interval 1, 2, 2, 3, and so on. So I have this kind of collection of subintervals. And this alpha is fixed. It depends on the porosity constant, ultimately, for us. It does not depend on H, on the high frequency constant. So then it turns out that for any F with the Fourier support condition, as before, you see that the mass of F on the union of all these intervals, all these holes, is bounded below by some fixed constant, depending on the nu and alpha, times the L2 norm of F. So that gives you the lower bound of what you remove. You see, when you're proving this kind of uncertainty principle, what are you optimizing over? You're optimizing over beta equals 0. So you're trying to improve over the unitarity of the Fourier transform. And so that's where, we use the unitarity of the Fourier transform in a way that the norm of F and L2 is the whole thing, and then we need to find a lower bound and get it removed. All right. So here's, I repeat the statement of the key lemma. Now, if we look at this key lemma from a point of view of classical analysis, you can see it looks like a unique continuation principle of sorts. If you look at the conclusion of the key lemma, it looks like a unique continuation principle. That it's a quantitative version of saying that your function f cannot identically vanish on these unions of intervals. Okay. So that's... And, unique continuation principles have been studied quite a while, but most unique continuation principles are known under the condition of decay of Fourier transform. So a basic example is, imagine that the Fourier transform of f was decaying exponentially fast. So if it's decaying exponentially fast, then f is real analytic. And we know that real analytic functions cannot vanish identically on subintervals, and you can use this to get an estimate like the one that we need. Now, it turns out that you can do a little bit better than that, in the sense that you don't need full exponential decay, and the specific decay that we use is drawn here. So it's e to the minus absolute value of xi over log absolute value of xi to the s for some s which is strictly less than 1. So it turns out that this kind of Fourier decay still gives you what's known as a quasi-analytic class. So you get something with unique continuation bounds. If s was equal to 1, or especially if s is bigger than 1, then you cannot use this kind of condition. So you really need it. It's a bit of a fine-tuned argument at this point, because you can actually use the theorem that I'll mention in a moment to show that for s bigger than 1, you can find compactly supported functions with Fourier decay like that. So it's kind of a curious dichotomy in terms of decay of Fourier transform. If your Fourier transform is decaying fast enough, then you have lower bounds on subintervals, so you have unique continuation. If your Fourier transform is not required to decay too fast, so if you change your weight in a certain way, then you can construct compactly supported functions in this range. And so there is something that I'm not going to state here, but this is the big tool that we use called the Berling-Malyamin theorem, which tells you that it gives you existence of compactly supported functions with Fourier transforms that decay if the decay is not too fast to put it in a quasi-analytic class. So it's actually a pretty sharp statement. And so what you can do is you can construct a compactly supported multiplier whose Fourier transform will have this forbidden decay, but only on the dilates of the set Y. So, we previously had something assuming decay of Fourier transform, but we don't have decay of Fourier transform in our assumption. Instead, we have a support condition in the Fourier transform, which is much harder to exploit. But so the way one can exploit it is one can construct a function which is compactly supported, and its Fourier transform is going to be decaying a lot, but only on this thin set. So that's where you use that Y is porous. And somehow it's a small enough set that you can arrange the function to have Fourier be compactly supported and have Fourier transform decaying a lot just on this thin set, but not in other places. All right. So this is this construction of a multiplier, and you can make it compactly supported as small as you want. In particular, I can make it supported in an interval, say alpha over 5, where alpha was the original size of this intervals I'm removing. And then the rest of the argument proceeds by taking the convolution of this function f that we're studying and the multiplier. And you see, because the multiplier has small support, convolving doesn't destroy our ability to get lower bounds on intervals of size alpha, because the support doesn't blur out all that much. On the other hand, because this multiplier has sufficiently rapid decay on the support of the Fourier transform of f, and because, of course, the Fourier transform of convolution is product of Fourier transforms of f and g, you see that the Fourier transform of the convolution has this rapid decay everywhere, and so you can use a quasi-analytic type bound. All right, so that's as much about the proof of the general theorem as I would like to say. Yes, there's a question. Yes. Mm-hmm. That is correct. That is correct. The key lemma is not a semi-classical statement. It's just the way I stated it before was Y was a union of basically H-sized intervals. And when you rescale it, what you get is you get a union of unit-sized intervals, which is distributed in a porous way on large scales. That's right. Yeah, this is not, there is no, the H effectively disappears at this point. But in the application, it's good to have X and Y play a similar role, which is why I stick this way. And then at some point, you iterate on scales, and so you don't just apply it to Y, but you apply it to kind of progressive coarsenings of the set Y. But that's part of the details that I added. So the scale lemma is applied on logarithmical Riemannian H scales. All right. All right. So yeah, so this was a kind of heavy harmonic analysis, at least as far as I'm concerned. I'm not a harmonic analyst by initial trade. All right. So now I'll mention one thing, but very briefly, is that actually in applications to quantum chaos, especially in applications to hyperbolic surfaces, what you need is actually a modified version of this Fractal uncertainty principle, where the phase in the Fourier transform is replaced by twice log of absolute value x minus y. So that's something that naturally comes from the geometry of hyperbolic surfaces. And so that's the kind of thing that you actually need to prove. And then this is a singular at the diagonal, and it does something at infinity, but it's actually, you can assume that you put a cutoff here that cuts away from a diagonal infinity. So it's a perfectly nice, as a semi-classical analyst would say, it's a perfectly nice semi-classical Fourier integral operator associated to something, and something turns out to be the scattering relation of the Poincaré upper half plane, which is kind of why it appears in applications to hyperbolic surfaces, compact and non-compact. So luckily for us, once you have Fractal uncertainty principle for the Fourier transform, you can actually reduce to it, or you can deduce from it Fractal uncertainty principle for this more general phase. And that part of the proof is not as difficult, but I will skip it. So I'll flash it on the slide, but I'll move on for now. I'll just say that the price to pay is that this exponent beta, which we don't really attempt to quantify, there is work by Jin and Zhang that actually tells you what beta is, but it's rather small, this beta. You have to divide it by 2 when you pass from Fourier Fractal uncertainty principle to the hyperbolic. All right. But instead of dwelling on that, let me move on to a setting which is easier to explain, and that's discrete countersets. So that's where I'll spend most of my time now. So this is a very particular class of fractal sets. It's certainly nowhere near enough to get applications to hyperbolic surfaces, but there are certain models, certain toy models called quantum Baker's maps, open quantum Baker's maps, where you can actually use literally this uncertainty principle to get a spectral gap result. So you can, if you're okay with working on more kind of toy model or made up models, then you can actually use this fractal uncertainty principle for something. All right. So this comes from earlier work with Jin, and there is I have these lectures on fractal uncertainty principle where that's the way the explanation comes from. So how does this work? Now, everything is going to be much simpler now, technically. So instead of taking Fourier transform on the real line, I'm going to take the Fourier transform on the on a grid. So I'm going to take a discrete Fourier transform, and here it is drawn. So n here is 1 over 2 pi h. I forgot to write, but so n is on the scale of h inverse. So h was small. This n size of the matrix is large. Okay. So here's the discrete Fourier transform. Right. This is a simple unitary matrix. Then what are the sets that I'm going to use? Well, they'll also be very simply constructed sets. You know how when you think about the Cantor set, you can think of it in terms of base 3 expansion of real numbers, right? And so you can think of it as numbers which have only zeros and twos in the base 3 representation, right? And so you can generalize this concept and get this discrete Cantor set, which is I just fix some base, m at least 3. I fix an alphabet, which is just a subset of points from 0 to m minus 1. And then I'll say my n, the size of the matrices or the size of the grid, will be m to the power k. So it's going to be this precise number, where k is large. So m is fixed, a is fixed, k goes to infinity. And then you just define ck as integers whose base m expansion only has elements in a. So for example, if m equals 3, alphabet 0, 2, then n will be 3 to the k, and what you get is this discrete mid-third Cantor set, which I wrote the first few numbers here. All right. So now these Cantor sets, they are porous. But they are more than that. You can actually have a well-defined dimension. One way to count this dimension is you just count the number of elements in this set, and you get n to the delta, where delta is just log of a base m. So, for example, for the mid-third Cantor set, you get log 3, 2 as the dimension, which is what you would expect. So here's an uncertainty principle for discrete Cantor sets, which is a statement that's similar to Theorem 1 before, but so assume that we have delta strictly between 0 and 1. So imagine that the dimension of my set is between 0 and 1. Those two cases are trivial cases. So if delta is equal to 0, it means your alphabet just consists of 1 point, so your set just consists of 1 point. And if your alphabet is the whole set, so if delta is equal to 1, then your alphabet is the whole set, and then your Cantor set is just the whole set of numbers from 0 to n minus 1. So then I claim that you have the following estimate. So you have this estimate on the triple product, where you just take this Fourier transform matrix and then you squeeze it between multiplications by indicator functions of this Cantor set, ck. Now, this is a very concrete object in a way. You just take the matrix of the Fourier transform. It's an n by n matrix. And now you just leave just the rows and the columns that lie in the Cantor set. Okay? So say if you wanted to code it up on a computer, it's very simple. You just take the Fourier transform matrix, and yeah, you just restrict it to rows and columns in the Cantor set, ck. So now you look at the norm of that with respect to the Euclidean norm, and that will decay as n to the minus beta. And what's beta? So we show that this works for some beta, which depends on the base and the alphabet. And this beta is positive, so that corresponds to the fractal uncertainty principle I stated before. But you can also improve over the volume bound, half minus delta, strictly. And so that's why I didn't want my set to consist of just 1 point, because if you have a set of a single point, then beta is equal 1/2, and you cannot improve that, right? So just like before, we have, we have counterparts of the kind of standard bounds. So you have the trivial bound beta equals to 0 because Fn is unitary. And then you have the volume bound. And one way to see the volume bound here, you can still use little LP norms, but another way is to use the Hilbert-Schmidt norm of a matrix. The Hilbert-Schmidt norm of a matrix is the square root of the sum of absolute value squares of all the entries. That's something that's actually invariantly defined for a matrix on an inner product space. And if you look at this Hilbert-Schmidt norm, you know that the operator norm is always bounded by the Hilbert-Schmidt norm. And this Hilbert-Schmidt norm is exactly n to the delta minus a half because, well, you just do the counting. Right, you have these entries, each of them, the absolute value square is 1 over n, and there is n to the 2 delta of them. All right, so these are standard bounds, and here's the statement of a discrete fractal uncertainty principle. So how do we show this? Well, a key property that we don't seem to have in general that helps simplify the proof greatly here is a submultiplicativity property. So if I say Rk is the norm of this big matrix, so remember my n depends on k, n is m to the power k. Right? So I have really a sequence of matrices, and I try to show some asymptotic bounds on the norm of this sequence. I want this to decay as a power of n, or I want it to decay as an exponential of minus something times k, equivalently. So it turns out that these norms are a submultiplicative sequence. So Rk1 plus k2 is no more than Rk1 times Rk2. So how do we show this? Well, I'll just do it briefly here. Because the proof, it's not going to be very instructive to showing more general situations, but it's a neat proof. And it's actually, it uses a decomposition of Fourier transform in terms, in the same way as what's used in the fast Fourier transform algorithms, at least in the most basic ones. So, how does the fast Fourier transform algorithm work? Well, the easiest situation, if your n was, say, a power of 2, and then what you do is you're trying to Fourier transform some vector. And then what you do is you split it into even and odd indices. So you just split you have the even part, so part corresponding to even indices, and then part corresponding to odd indices. And then each of these parts, it has a certain symmetry property. And using that, you can reduce the computation to computing things for even and odd separately, and that's how you can make it work in time n log n as opposed to usual n squared. So that's what we do here. Instead, however, instead of writing even and odd, we write our n as a product of m to the k1 and m to the k2, and then you identify any vector with an n1 times n2 matrix. Okay, so when you do even or odd, then one of those numbers will just be 2, so it will be like n is equal to 2 times n over 2, but here I write n as a product of two numbers. And so if I have an n1 times n2 numbers, I can write them as a matrix. And I can write it actually in two different ways because I can choose where I put the rows and the columns. But anyway, so I represent it as a matrix. And then I apply a Fourier transform in n2 on the size n2 grid to each row of this matrix. I multiply by twist factors each entry. These twist factors have unit size. And then I apply the Fourier transform to each column of the matrix, now in n1 size. And the resulting matrix gives me the Fourier transform of the original vector. I think that's a pretty neat general thing that, as I said, also appears in FFT. So you can effectively write your Fourier transform on n1 times n2 as a kind of product of tensor products, so as a tensor product of Fourier transforms modulo those twist factors. Now, if you look at what happens with this restriction to fractal sets, well, my fractal set would just correspond to the, if in this matrix, it would just correspond to rows and columns being, again, fractal sets of smaller dimensions. just because it's arranged this way. So for example, if I take mid-third Cantor set and I take k equals to, let's say, 4, so I write my elements there as 9a plus b. Now, if I have 9a plus b in the Cantor set of order 4, that's the same as a and b both lie in the Cantor set of order 2. And so you can see that this process actually respects very nicely how, how this indicator function works. And from there, you can see that you get this, this submultiplicative bound, because you can write your operation in terms of the lower order operations here. And you apply one, then you apply something unitary, then you apply the other. And so the result is going to be, the norm is going to be bounded by the norms of these operations. And here's an example. Maybe I should skip it, but well, maybe I'll say it briefly. So there's the most silly example of this procedure, which is n equals 4, which is 2 times 2. And then you have a vector, u0, u1, u3, u4. And then if you follow the instructions that I had before, you just take this vector, you arrange it as a matrix like this. Then you apply Fourier transform to each row. Then you get this matrix. Then you multiply by twist factors, which here just would mean multiplying this bottom right entry by I, it turns out, minus I. And then you take a Fourier transform of each column. So I said, I'll pause the slide, so I'll leave it to you to check this computation. And then when you do this, when you unpack this back, you will see the Fourier transform of the original vector, but now of order 4. But you used the Fourier transform of order 2 before twice. Right? So that's kind of neat. All right, so how do we use it to show fractal uncertainty principle? So we have submultiplicativity. Now, if we have a submultiplicative sequence, you see that all of your arcanes are bounded by 1, right? Because they are just these norms, and this is unitary, and the rest are bounded by 1 and 1, right? Now, I want my sequence to be exponentially decaying in k. Well, for that, I just need to have one term of this sequence to be strictly less than 1. Right? Say, imagine that I knew that, say, R10 is less than 1. Well, how do I estimate, say, R100 or R1000? R1000, well, it's going to be no more than R10 to the power 100 by the submultiplicativity bound, right? Because I just tried 1,000 as 10, added to itself 100 times. I apply this bound. And so I see that if my let's say R10 was less than 1, then any multiple of 10 would just be decaying exponentially according to that. And that's enough to show this exponential decay, or power decay as far as the original line is concerned. So you reduce to something that looks much simpler. Instead of studying asymptotics, you just need to show there exists one value of k, one value of the order of Cantor set, large enough, so that this norm is strictly less than 1. Now, if we're looking at this, it becomes a neat problem, actually, that you have a matrix, and its norm is bounded above by 1. And you need to just exclude the situation where the norm is equal to 1. Now, when you look at this matrix, well, what do? We take a vector, we kill everything that's not in the Cantor set, right? We multiply by the indicator function. Then we apply unitary operation for a transform. Then we again kill everything that's not in the Cantor set. Now, if the norm of this matrix was equal to 1, this means there is, it's a finite dimensional matrix, so there is a vector maximizing this norm. And then for this vector, you see that it had to be supported on the Cantor set, because otherwise this first operation would reduce the mass by some number, and that's gonna make it strictly smaller. And then for similar reasons, the Fourier transform has to be also supported on this Cantor set. So what you should rule out is the existence of a non-trivial vector, which literally is supported on the Cantor set, and its Fourier transform is also supported on the Cantor set. Right? So that's, again, this submultiplicativity is neat because it reduces an effective asymptotic bound to actually just showing, kind of ruling out this particular kind of counterexample. Of course, for general sets, this counterexample can and does happen. A basic example would be if one of my sets here was a subgroup of Z mod n, and the other set is a dual subgroup. Then if you take the indicator function of the subgroup, the Fourier transform will be the indicator function of the dual subgroup. But our sets are fractal, so they don't look like subgroups, and that's something that we use. So how do we rule this out? And that's where we use just a tiny bit of algebra, elementary algebra. So if you think about the Fourier transform, one way to think about the Fourier transform, the discrete Fourier transform, is evaluating polynomials at roots of unity, right? So this is, this proof really uses kind of standard Fourier transform theory, the discrete one. So let's form a polynomial in complex variable with coefficients which are the just the entries of this vector u of l. Then you know that the Fourier transform of u at a point j corresponds to, well, a prefactor times this polynomial applied to jth root of unity. Right? That's how discrete Fourier transform works. Now, now what we do with this polynomial is we'll just count its degree and we'll count its number of roots. So for degree, let's assume for simplicity that my alphabet doesn't contain m-1. So my alphabet is not everything, right? So there is at least one digit that doesn't lie in the alphabet. Now it's convenient to me that assume that this digit is not the last digit. Otherwise, I can shift my set around circularly, but let's just assume I don't have the last digit. So then what's the maximal degree of P? Well, the coefficients have, the powers have to be numbers in this Cantor set. So the degree of P is bounded by the maximal number in the Cantor set. Now here's a basic question. Let's say M is equal to 10 and K is equal to 3. So what's the largest 3-digit number which doesn't have any 9s in it? It's 888, right? Well, I don't need such a sharp bound, but it's certainly no more than 900, right? We can agree on that. And so you can see in general that the maximum element of the Cantor set will be no more than m to the k times 1 minus 1 over m, right? Just because the first digit cannot be, it's in the alphabet, and so it cannot be in this, m minus 1, okay? So that's an upper bound on the degree. So you see that you're missing a kind of a positive fraction here because m is fixed and k goes to infinity. On the other hand, I have a lot of roots of this polynomial because I see that my Fourier transform of u is localized to this Cantor set. Well, what does this mean to be supported in this Cantor set? It means it's 0 on all points not in the Cantor set. And so you have how many points in the Cantor set? Well, you have ck points. You have size of ck points in the Cantor set. You have n minus size of ck points not in the Cantor set. And each of these, if you look at the corresponding root of unity, it gives you a root of the corresponding polynomial. So the number of roots is at least n minus the size of the Cantor set. Now, here's another question. So if you have, again, 3-digit numbers, and you look at how many digits, how many 3-digit numbers we have, a base 10, so that no digit is equal to 9. So the answer is, again, the answer is different. It's 729, right? Because what you can have is that you have k options, right? And each time you can only choose out of m minus 1 options for digits. So 729 is 9 cubed, but it's France, so I'm sure everybody knows that by heart. So yeah, so you see that this is the number, this is the lower bound on the number of roots. And so you can write it as m to the k times this expression. And then when you compare it, you see that when k is large enough, the number of roots will be bigger than the degree, and that cannot happen. And so this means, this gives you a contradiction. This means that rk is less than 1. All right? Okay. So let's see how much time I have. What was there? Oh, okay. Just checking. Maybe I'll discuss this for just 1 minute. Here's another part of the statement. So I also promised you that we can get Fractal uncertainty principle with beta strictly bigger than half minus delta, assuming that my alphabet has at least 2 distinct elements. So this is this is actually a really baby version of something known as Dolgopets method in dynamical systems. The original Dolgopets method is quite subtle and complicated, but this version is easy to explain. So similarly to the previous slide, it's enough to show that you get an improvement over n to the delta minus a half at one value of k because of submultiplicativity. Now you see this n to the delta minus a half is the Hilbert-Schmidt norm of my matrix. So now instead of using elementary polynomial algebra, I'm going to use elementary linear algebra. So assume that my norm was actually equal to n to the delta minus a half. So this means that the operator norm is equal to the Hilbert-Schmidt norm. Now think as an applied mathematician, think in terms of singular values. So in terms of singular values, the operator norm of this matrix, the operator norm is the maximal singular value, right? And the Hilbert-Schmidt norm squared is the sum of squares of the singular values. That's their interpretation in terms of singular values. So, okay, singular values are positive or not negative. So you know that, so you have a situation where you have a matrix and the maximal singular value is equal to the little L2 norm of the vector of singular values. The only way this can happen is if there is at most one non-zero singular value, right? If at least two singular values are non-zero, you see that this Hilbert-Schmidt norm will have to be strictly bigger than the maximum. Well, but what does this mean that you have? Well, if you have no non-zero singular values, your matrix is just zero. What if you have just one non-zero singular value? Well, what this means is that your matrix has rank 1. And if your matrix has rank 1, then following, this old kind of classical courses in linear algebra that many of us probably took back in the day, rank 1 means that any 2 by 2 minor, so any determinant of kind of a 2 by 2 submatrix is equal to 0. And so when you compute it, you will see this condition, that for any 4 elements in the Cantor set, you get this kind of product, and it has to be n times an integer. It's a fun computation, so I'll leave it as an exercise rather than clearing it out. And when you look at it, it cannot happen when k is equal to 2, because you can just see that you can just take two pairs of elements of the alphabet, the same. So j is L, j prime is L prime, and this j minus j prime, you can make it non-zero, but strictly less than square root of n by just fixing one of the letters to be the same, the first digit to be the same, and the second digit to be two different things. So for example, if I'm looking at base 10 and I only allow, say, digits 1 and 7. Okay, well, I'm going to take 11 and 17. And what's 11 minus 17 squared? I think it's 36, but I don't really care. What I care is that it's certainly less than 100, right? And so it's strictly less than n. And so this thing, if it's positive, it cannot be an nz. All right. So that's this. Oh, am I out of time? Here you need delta bigger than 0. So when delta, so you get this upper bound delta minus a half for all deltas. The bound stops being interesting when delta is bigger than a half, but that just means, well, you still can improve over it. It's just much easier to improve over it. When delta equals to 0, this upper bound turns out to be sharp. But when delta is positive, so your alphabet has at least 2 entries, then it turns out you can always improve over it. So it's like, morally speaking, it would be like improving over the entropy bound. But again, nobody ever figured out how to actually make this analogy a reality. But yes? Right. Right. So previous I was showing you can get beta bigger than 0. Now I'm showing you can get beta bigger than half minus delta. Yeah. And that's what I was doing. And this is kind of a baby version of what's known as Dolgopet's method. All right. So here I think there's the left slide about the 1D discrete case. And so here's a picture of fractal uncertainty exponents numerically computed for all alphabets with m no more than 10. So this just shows you how complicated the situation can get in a way. So the horizontal axis is delta, the dimension of the fractal set. So it's log the size of the alphabet over log m. The vertical axis is beta. It's the fractal uncertainty exponent that we get. And now you see that you get the solid line is the standard bound, so kind of the quote-unquote trivial bounds, or the horizontal line here is beta equals to 0. So that's the trivial bound. And then there is the volume bound, half minus delta here, right? So the solid black lines is what you get what you get automatically without much work. The dashed line corresponds actually to a conjecture by Jakobsen and No, and that's the best you can get in some sense. This is half minus delta over 2. And then you see the plot, and it actually kind of fills out this triangle quite neatly. So you can see on the left, this is what I was talking about, this improvement over half minus delta. You can see those triangles, they get pretty close to the line, but now they don't lie on it. On the right, it really looks like these points lie on the line, but they actually don't. Like if you consider one of those, I think the bottom of these yellow triangles is of the size 3 times 10 to the minus 7. So it's a positive number. A computer can tell you it's positive, but your eyes can't. And that's just for an alphabet, or maybe, oh, sorry, the plus here, this plus is, and that's already for an alphabet of size 4. So these fractal uncertainty exponents, they can get very small, at least in this kind of very symmetric situation, but they're still positive. And then, yeah, you have a whole zoo of what happens there. Now, let me quickly move on to, I think I have a couple minutes to discuss the higher dimensional versions of fractal uncertainty principle. So an open problem is to get a fractal uncertainty principle for subsets of Rn where n is bigger than 1, with beta bigger than 0. So you can restate, let's just take dimension 2. That's hard enough already. So we have this semi-classical Fourier transform. We want this kind of bound as before, and now we want x and y to be, well, I didn't define delta regular, but let's say they have dimension delta effectively, less than 2, or you can think of them as being porous. Now, that's a very difficult statement to prove because it's false. So it's unless you unless you do certain kinds of logic, I think. Even if you do certain kinds of logic, proving false statements is hard. And here's why it's false. And the counterexample is very simple. In the limit, it just looks like one of the sets is a vertical line and the other set is a horizontal line. If you take a delta function on a vertical line in R2, what's the Fourier transform? The Fourier transform is going to be delta function on a horizontal line. That's what it's going to be. And so you have an example of a function with Fourier transform on a line, or distribution really, and the Fourier transform of the Fourier transform is so the support of the distribution is on one line, and the support of the Fourier transform is on the opposite line, and the line is a porous set. Now exercise: any line in R2 is a porous set with porosity constant 1/2. Namely, in any ball of size r, you can find a subball of size r over 2, okay, maybe minus epsilon, which doesn't intersect this given line. And so that's unfortunate. And if you wanted something that corresponds to this particular version of uncertainty principle, then you just fatten your lines by size h things, and you can cut them off to make them compact to support. So you have a kind of a thin vertical rectangle and a thin horizontal rectangle, and you can see that you cannot get beta bigger than 0 here. So there are certain advances on that. So Hahn and Schlag showed that you get a fractal uncertainty principle if one of the sets is contained in the product of two fractal sets, which is in general rare to happen for a fractal set to be contained in the product of two fractal sets. And there is a conjecture that actually the hyperbolic fractal uncertainty principle should still hold. So the one with this other phase. But it's it's widely open. It would be very nice to have, because that would give strong implications to quantum chaos. But we don't know this yet. There is some work in progress with myself and Jean, where one of the sets is a curve. But somehow this hyperbolic fractal uncertainty principle, you cannot make up this counterexample to really work. So there's some hope that maybe it is true, but we don't know why. But here, let me present you an exciting result. Very recently, actually, just earlier this year, about the two-dimensional fractal uncertainty principle for discrete countersets, so the setting that I discussed at length before, but now in 2D. So I'm going to fix a base. Now I'm going to fix an alphabet, and it's going to be a subset of z mod m squared. So here's an example. When m equals 3, here's my alphabet. So I click some rectangles and not others. And then I define my Cantor set in the same way. And so I just subdivide each of the black rectangles according to this pattern and keep going. So here's an example. So you start with this. Here's k equals 2, right? Here's k equals 3. Hopefully, Collège de France has good resolution screens. K equals 4. And here's k equals 5. Right? So you get a set that looks like this. Looks kind of neat. And this is kind of a basic example of a set like that. Oh, here's k equals 6. Now that's challenging, right? To plot. Okay. So now here's a theorem. So this one is due to Alex Cohen, who is a second-year graduate student at MIT. And what it says is that you have a fractal uncertainty principle for these sets unless the limiting Cantor sets contain two orthogonal lines. So basically, there is a dichotomy. If you have a situation that one of your sets, one of your Cantor sets contains a line, and the line, you should think of this as a subspecies of the torus, so this would be rational lines, so it would be subtoric, it can wrap around. And the other set contains an orthogonal line, then you can easily see that fractal uncertainty principle fails. For kind of same reasons as explained in the example before. But if you do not have this situation, so if you do not have rational lines in this set, orthogonal to each other, then the fractal uncertainty principle holds, which is very neat. I should say the way you could contain lines could be complicated. For example, for this set, it actually contains quite a few lines. For example, it contains this line going like this and like that, right? When you wrap around the torus, this counts as a line, right? So for example, this set, it does contain lines. But most Cantor sets do not contain any lines at all. So here I can see 3 lines, right? You can see this kind of hexagonal shape. I guess it's the Star of David, but you can see this kind of hexagonal shape, and it's really 3 lines in the torus in this particular example. So how does Alex prove it? Well, I don't have time and maybe the mental capacity to explain how it works, but I'll just say 2 things. One is that submultiplicativity still holds in this setting. So it's enough to show that you have no counterexamples. You have no function or no vector that's supported on one of the sets, and the Fourier transform is supported on the other set. However, the statement is much harder to prove in dimension 2 than it was in dimension 1. In dimension 1, we use degrees of polynomials, that the polynomial doesn't have more roots than its degree. But in dimension 2, the study of polynomials is much harder, right? That's why you have to start bringing in some algebraic geometry there. And the proof does use in what I think are ingenious ways algebraic geometry and actually some number theory. And the key ingredient is a quantitative version of what's known as Lang's conjecture and cyclotomic points on algebraic curves in C2. So this Lang's conjecture tells you that if you take C2, so C squared, and then you look at the torus, so you just take the pairs Z and W, complex numbers, so that absolute value Z and absolute value of W are both equal to 1. So kind of class standard embedding of the torus into C2. You have cyclotomic points on this torus, which means that Z and W are both roots of unity. Lang's conjecture tells you that if you have algebraic curves, so a 0 set of a polynomial, then either this algebraic curve only has finitely many cyclotomic points, so there's only finitely many Z and W's roots of unity, so that solve this polynomial equation, or this polynomial that's defining this curve has a factor which effectively corresponds to a line in a torus, and that's why lines come up as counterexamples. And so there's a quantitative version of that due to Rupert and Boyker-Smith, and that's the essential ingredient analysis proof. All right, I should really stop now. Now I should have run over time. Thank you for your attention.